Okay, so in this video we're going to have a look at an application of Rouché's theorem. So you might have heard of the fundamental theorem of algebra before. And the fundamental theorem of algebra says every polynomial of degree n can be factorized into n linear factors. So for example, a polynomial of degree 2 like x squared plus 2x plus 1 can be factorized into x plus 1 times x plus 1. There's two linear factors. Okay, so now let P be a general polynomial. A is n x to the n plus a n minus 1 x to the n minus 1 dot 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 all the way to a1x to the 1, or just x, plus a naught, and then x to the naught would be just be 1. And we can write in shorthand something like this. And we want to show that this has n linear factors, or n roots counting repeated roots. The way we're going to do it, again, is with Rouché's theorem, but Rouché's theorem tells us a little bit more than the fundamental theorem of algebra. It not only tells us that there are n roots, but around about where it is. Rouché's theorem tells us that the roots are in the open ball centered at 0 of radius r, where r is, for these constants, it's equal to 1 plus the sum from k equals 0 up to n of the absolute value of these constants. And these constants are complex numbers, so ai are complex. They can be real, but in general they're complex numbers. How do we prove it? To satisfy the conditions of Rouché's theorem, we're going to check that this set is a simply connected domain, and it is. And the second thing we're going to check is two polynomials for us to use the theorem on. And it turns out the polynomials you should use it on are f is equal to this leading term, which is an x to the n, and g is equal to this remaining term, which is, and in this case, because we want it to be degree n, an is not equal to 0, right? Because we want p to be of degree n. And because an is not equal to 0, this has n roots counting repeated roots, or n linear factors. G, we want to be the rest of it, so an minus 1 x to the n minus 1 plus dot 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 plus a1x plus a naught. So Rouché's theorem says that if these two are analytic and the absolute value of g is less than the absolute value of f on the boundary of this ball for all absolute value of z equals capital R, which is the boundary of this ball, then this being true implies that f and f plus g have the same number of zeros, or same number of roots inside this open ball. But we know that f has n roots inside this open ball because all its roots are 0. So f and g have the same number of roots in here. That means f plus g, which is our polynomial, has n roots, has the same number of roots or zeros, i.e. n, right? N roots. So the only thing we have left to show is this part. This is the main thing we need to show, which is kind of what makes proof by Rouché's theorem look so magic. This thing, which seems completely unrelated to the actual theorem, we're just showing that one function is less than the other, and suddenly we have the fundamental theorem of algebra. So let's check this fact. We're going to check that g is less than f. So let's actually write the absolute value of g. The absolute value of g is equal to the absolute value of this sum. So the absolute value of the sum. And now we're not summing to n, we're summing to n minus 1, k, a k, x to the k. And using the triangle inequality, we can actually bring the absolute values inside the sum. So I'm using x's, but this is complex analysis, so it should all be z's. So I'll just switch to z right now. Just sorry about that. And this is less than or equal to the sum of k minus 1, absolute value of a k, z, k. And we can split this up as well. So this part would just be absolute value of a k z to the k, just this part, z to the k like this. Here's the part where we need to just think a bit harder. So there's r, and we know it's 1 plus something positive. The z, that's the absolute value of z, which is equal to r. So z is bigger than or equal to 1, and when we raise something bigger than or equal to 1 to any power, it's just going to become bigger. And so the biggest it can be is n minus 1. So what we're going to do is we're going to just make all these terms n minus 1, and so make the sum greater. So we'll make the sum greater, so greater than or equal to sum k n minus 1, absolute value of a k, absolute value of z to the n minus 1. So we've just made the sum greater by replacing these zk's by zn minus 1 because the z's are bigger than 1. Now, this zn no longer has any dependence to k, which we're summing over, so we can actually factor it out. And now you might notice something, that over here we have this sum, and over here we have this sum, and they kind of look similar. We know that r is bigger than this, and so we're going to use that fact. And we need to remember this as well. We said the absolute value of z is equal to r, and so this is r to the n minus 1, and so this is equal to r to the n. Okay, so it looks like I made a very slight mistake. So this over here, this r should have been r to the n minus 1 divided by a naught. It doesn't make much of a difference actually. So for the first part, when we used r, we used that absolute value of z equals r. We just wanted this to be bigger than 1, but this doesn't actually change the fact that it's bigger than 1. And the reason we want this to be true is now if we multiply both sides by an, we see that absolute value of an times r is bigger than this because we're adding on some positive amount. So we have that absolute value of a naught, r is bigger than this sum. And so this is equal to the absolute value of a naught, r to the power n, and this is equal to the absolute value of f, because f is, well, this would be z, but absolute value of f would be absolute value of a n, absolute value of z to the n, but absolute value of z is r, and so this is equal to the absolute value of f, and we've shown that the absolute value of g is less than the absolute value of f. So we've satisfied the conditions for Rouché's theorem, and so f and f plus g, which is p, have the same number of roots on n. So thanks for watching. See you next one.